Let's start.
Okay. Hello everyone. Welcome to IIT Gate classes. So, so as you know, IIT Gate classes uh, is for ME for aerospace, mechanical, and multiple branches. There are different courses which are offered here. So you can go to the website and check more about it. So today, I am Pradeep here, and I have been associated with IGC from last 1 year. I did my master's from Indian Institute of Science, and today we will be talking about thermodynamics. Okay, so we will cover basics of thermodynamics. So let's get started. So when we talk about thermodynamics, the building blocks of thermodynamics are basically we start with few basic definitions. So we start with that. So most important definition when we start thermodynamics is the definition of the system. So there is a concept which comes first and foremost is system. What is system here in thermodynamics? Okay, system is basically defined as a quantity of matter or a region of space that we basically choose for the purpose of analysis. Okay, so let us say, so this is the region of space that we select for the purpose of analysis or for the purpose of study. So anything inside this boundary, the matter which is inside this boundary, it constitutes our system. Okay, anything outside this boundary is basically called as surrounding. So inside the boundary, the matter that we select is called as system. Okay, external to the system, the matter what is available there, we call it as surrounding. System and surrounding are basically separated by a boundary, and this boundary is called as the, you can call it as a system boundary. This is a pretty abstract definition. Let's look into a practical scenario. How do we look into a system here? What is a system? So let's say you have a piston cylinder arrangement. So this is your boundary of the cylinder. Okay. And this is the piston that you have. Okay. Now behind this piston, you have a gas. Okay. And let us say you are heating this gas. You have a burner and you are heating this gas. Okay. Your objective is you want to study what happens to the behavior of the gas when you are supplying heat to it. Okay. So in thermodynamics point of view, if we want to focus our attention on the gas, okay, then gas becomes our system. And so the gas behind this piston cylinder arrangement becomes our system. So we demarcate the system by drawing a boundary. Okay. So this dotted line which I am drawing right now, it becomes the boundary. So this becomes the boundary. Okay. The gas behind the piston cylinder arrangement which we are trying to study, this gas becomes our system. And everything external to this dotted boundary, it becomes surround. Okay. Now, this is one particular example of the system that we are talking from a thermodynamics point of view. There can be other practical scenarios where you can look into the system. For example, your iron box. Let us say you have an iron box here. Okay. Okay. Let us say this is the wire here. Okay. Now what you do, you switch on the iron box, and as you switch on the iron box, you would have observed that after some point of time, let us say this iron box initially was at an ambient temperature T infinity, which might be 25 degree or 30-degree depending on the room temperature. As soon as you switch on the iron box, okay, After a certain period of time, the temperature changes to a different temperature. Let us say T1. Okay. Your objective is you want to know that after certain energy or certain rate at which you are supplying the energy, how much the temperature of this iron box will change. You want to determine this thing. So then, if you want to determine these things, what becomes your system? So you basically select your iron box as your system. Okay. So this dotted line, which encloses this box inside, okay, then it becomes our system boundary. And this box, iron box, becomes our system. Okay. And then we can perform thermodynamic analysis, okay, of the iron box to predict what will be the temperature of the iron box after certain period of time. Okay. Similar example can be an example of a microwave oven. Okay. Let us say you have an oven. Okay. And inside the oven, let us say you are keeping a bowl of rice. Okay. Your objective is you want to find out how much time it will take to heat this bowl of rice. Okay. So what you can do is that for the purpose of this thing, then we want to focus our attention only on this bowl of rice. Okay. So what, and it becomes our system. So we demarcate our system then by drawing this boundary. Okay. So everything inside the boundary or the matter inside the boundary, it becomes the system. And matter which is external to the system becomes surrounding. And system and surrounding are clearly demarked by a boundary which is called as a system boundary. Okay. So what is system? System in short is basically a quantity of matter in an abstract definition. It is a quantity of matter or a region in space on which we are focusing our attention for the purpose of analysis. For example, in this case, we have gas behind the piston cylinder arrangement. We are heating it. We are focusing our attention on the gas. We want to analyze the gas behavior. What happens to the pressure of the gas? What happens to the temperature of the gas? How the volume of the gas changes when we are heating it. In this case, our system is the this basically iron box. Our objective is we want to analyze this iron box and want to understand what happens to the iron box as soon as we switch it on. Okay, so the iron box, okay, this matter, iron box, it becomes our system for the purpose of analysis. Okay, similarly in thermodynamics, there can be different practical scenarios where we can select different systems. Okay, now let's understand another concept. We talked about the that you have a system and you have surrounding, and system and surrounding are separated by the system boundary. Okay. Now what can we think about this boundary? Okay. Is this boundary always fixed? Is this system boundary always fixed, or it can change also? Okay. Now when we are talking about thermodynamics and when we talk about system, there is no constraint as such that the boundary of the system has to remain fixed. Okay. The boundary of the system can change with respect to time. Okay. So for example, let me give you another example. So the same example here, the gas behind the piston cylinder arrangement, we are heating it. So what will happen? As you are heating the gas, what happens to the gas? So gas becomes heated, it expands, okay? And you have marked the boundary of your system by this green colored dotted line, right? As the system, as you are going to transfer heat to the gas is going to get heated, the gas will expand. And once the gas will expand, the volume of the gas behind this piston cylinder arrangement is going to increase. In that case, what do you see? You see that the boundary or the system boundary is no more constant, it is changing with respect to the time. So the boundary which is attached to this face of the piston, it is going to change. So the boundary, system boundary, it can be fixed or it can change with respect to time, or it can move also with respect to time. So that's another thing. Now let's go ahead and look into different types of systems. What are the different types of systems that we can have? Okay, so So we talked about system. Okay. Now, how many types of systems can we have in thermodynamics? So in thermodynamics, there can be two types of system. Okay. So one system, we defined one system as closed system. So what is a closed system? Okay. So closed system is a system in which, let us say you have, again go back to the definition, basic thing. So you have this system or a region of space on which you are focusing your attention, and you have your surrounding. Okay. So when we are talking about closed system means, as the name implies, it is closed. Closed means between system and surrounding, there can be no mass transfer. When we say mass transfer, that means there can be no mass which can come from the surrounding and enter into the system. So the mass of the system is going to remain fixed when we talk about the closed system. That's why closed system is also called as control system or a control system. Why? Because the mass remains the fix. Example, let's say, again look at the same example that I talked about, the piston cylinder arrangement. So this is the cylinder that we have, and this is the piston. Okay. And we are considering the gas behind the piston cylinder arrangement. Okay. Look at it. Okay. If you look at this gas, it is bounded by a closed boundary, okay, around it, and there can be no mass which can come inside because it is completely sealed from all the sides. Okay. So this system, which is our gas, which we are focusing our attention for the purpose of analysis, this system is then behaving like a closed system, or it is a closed system because there can be no mass transfer that can happen inside this system. No mass can come inside, as well as no mass can go outside. So this is an example of closed system. Now, let's say if you create an opening here, you create a small opening here. Okay. Let's say you are creating a small opening here. Then what happens? Okay. So if you create a small opening, in that case, now mass can enter into the system and mass can go outside the system also. So that kind of a system is called as a open system. Okay. That system is called as an open system. Okay. So what is a closed system? Closed system, there is no mass transfer or no mass transfer. No mass transfer between system and surrounding. In case of open system, there will be mass transfer between system and surrounding. Examples, more examples, if you want to look into the case of an, we will look into the case of an open system in more detail and understand it. Okay. So now we have looked into the open system definition and the closed system definition. Okay. An example, let's say another examples of open system. What are the different examples of open system? One example, I have given you a piston cylinder arrangement where there is an opening, mass is coming in and going inside. Then let us say you are studying a heat exchanger. When you are studying a heat exchanger, under that condition, what happens? So in case of heat exchanger, okay. So heat exchanger is what? Heat exchanger is basically a device in which you will have hot fluid entering the system, cold fluid entering the system, and hot fluid leaving the system. That kind of a system we are talking about basically. So let's say you have this kind of an arrangement. Okay. In this case, what can happen? The fluid can come inside and the fluid can go outside. Okay. So in this case, what happens? Mass is coming inside the system and mass is going outside the system. Okay. So this kind of system is basically called as an open system. Okay. Examples of open systems are basically your heat exchangers, turbines, compressors. Okay. Now, once we have understood the idea of system, closed system, and open system, let's move to the next topic here. So, next topic is how do we study our system? How do we define the system basically? What are the characteristics of the system? Let's say you have selected your system. How do you characterize the system? Okay. So, in order to characterize the system,
Sir, one
yeah, Dinesh, is there a question?
so I had a one. I had a query. After this, you can
Mhm.
explain how exactly thermodynamics will be useful in mainly in applications like turbo machinery and other stuffs from mechanical perspective also and aerospace perspective. Yeah, please.
Okay.
Yeah,
So
please continue.
let me just, yeah, so let me take that question and I can probably little bit build on that. So let us say when you are doing the analysis of, let us say you are trying to design a turbine. Okay. Let us say an axial flow turbine. You are trying to design a, if you are trying to design a turbine, the purpose of the design is that what a turbine does. So turbine basically produces what it does. It produces shaft work. Okay. So it basically develops the power and that power is basically used to run certain other components. Okay. So how does it develops power? Okay. So if you look at the example in case of a turbine, let us say you are studying turbine. So in turbine, what happens? So in turbine, what happens? You have fluid. So it is an open system. There is a fluid comes into the turbine. Okay. This fluid which is coming into the turbine, it comes in with very high energy. Okay. And then the fluid which is leaving the turbine, it goes out with comparatively lower energy. Okay. So this change in energy of the fluid which happens inside the turbine, okay, that finally gets converted into what is called as a shaft work. Okay. And this shaft work is then used for different purposes. Okay. So for example, turbines, it is used for, if you look at the basically the steam power plant, they are basically used for what? Those turbines are basically used to produce electricity. And basically this energy of the fluid which is getting converted into the shaft work is finally getting converted into electrical power. Okay. So there thermodynamics comes into the picture. Now question is how it comes into the picture. So how thermodynamics comes into the picture is that you have a hot fluid or a fluid with a higher energy coming inside, a fluid with lower energy going outside, and finally it gets transfers the energy to the shaft. How it happens? You have a rotating shaft, on a shaft on which you have different kind of blades which are mounted on it. And when the fluid flows through these turbine passages, basically what happens? The fluid undergoes an expansion process. And during that expansion process, what happens? It does work on those turbine blades, and turbine blades does work or it transfers energy to those turbine blades. Okay. because when it flows through the blades, there is a rate of change of momentum that happens for the fluid, and that finally gets transformed into the force, and that way it tends to rotate the turbine. Okay, so that's one example. Similar example is basically the example of a compressor. Okay, basically the axial flow compression. So there also it comes into the picture. Okay, so we will basically look into the different, when we look into the first law of thermodynamics, probably at that time it will become more clear how that first law, that is law of conservation of energy, is basically, which is coming from thermodynamics, is basically driving the working mechanism of these devices. Basically how that is being used for calculate some performance parameters which are absolutely critical for the design of these devices. Okay, so right now we talked about system, we talked about open system, closed system. So turbine and compressors are examples of the open systems. Now we were talking about one important thing, is that how do we characterize the system? Okay, how do we characterize the system? So let us say this is our, basically the region which we have selected for the purpose of analysis. How in thermodynamics this region is characterized? So as I told you, this region can be a fluid behind a piston cylinder arrangement. So how do you characterize this system? So this region is characterized by its properties. Okay, measurable properties. What are those properties? If you look at the gas, the properties can be the pressure of the gas, okay, can be the temperature of the gas, and the volume of the gas. Okay, likewise there can be different properties that are there. So properties are what? Properties are basically the characteristics of your system. Okay, and once you fix these characteristics, so for example, again we go back to the same example, piston cylinder arrangement. We look into the gas behind the piston cylinder arrangement. Okay, once you fix the properties of the gas, right, once you have fixed the properties of the gas, okay, let's say you have fixed the pressure and temperature of the gas, then we say that we have fixed the state of the gas. That means we have defined, we can clearly define what is the condition of our system. Okay, so properties are what? Properties are the characteristics, and when these characteristics are fixed, we can clearly define what is the condition of the system, and that condition of the system is called as the state of the system. Okay, and when any properties of the system changes, we say that the system has undergone a process. Okay, so how do we understand that? So let us say we draw a graph here. Okay, on the x-axis, let us say we have volume, and on the y-axis, let us say we have pressure. Okay, and this is the gas behind our piston cylinder arrangement which we are considering right now. Okay, and at this condition, when we start, right, let us say we know what is the pressure and the volume of the gas, then we can clearly define the state of the system. So this point here, which tells us what is the pressure and temperature of the gas at state 1. Okay, so it is clearly defining the state 1. Now let us say we start heating the gas, we start transferring energy to the gas, and this gas expands and it tends to move. Then what happens as the gas is moving? Okay, as the gas is expanding and the piston tends to move, what happens? The volume of the gas keeps changing. Okay, and the piston moves outward. Okay, then what we can do is that at other locations also we can again measure the pressure and the volume of the gas. Okay, likewise we can define pressure and volume of the gas at different conditions when the piston is moving. Okay, so all these points which are basically defining the state of the gas at different positions, these are the state points. Okay, okay, and when you connect all these state points by a curve, okay, what it represents? It represents the entire process that the system undergoes during this change of state. Okay, so this is the process which the system has undergone when the gas, which is our gas, is our system here, when the gas is expanding, when we are heating the gas. Okay, so now we have understood what is the state, we have understood properties and the process path. Let's say, how do we calculate work transfer? What is work transfer in thermodynamics, and how do we calculate the work transfer? Okay, let's go ahead. So, in order to understand the work transfer part, right? So, we talk about the displacement work. So, what is the displacement work here? Let's take the same example here and we will understand this thing here again with that. Okay. So, we have gas behind the piston cylinder arrangement. Okay. So, this is our gas. Okay. Let's draw the PV diagram here where P is our pressure and V is our volume. So, this is our pressure. This is the volume. Okay, at these conditions we know what is the pressure of the gas and we know what is the volume of the gas. So we can clearly define what is the state of the gas corresponding to this condition. So let's mark that point. So this point is the state of the gas corresponding to this condition. Now let us say the gas in this behind the piston cylinder is expanding and piston is now moving to different positions. So let us say this is the position of the piston at after some time. So piston is now moving. What we are doing is we are tracking the at each and every instant we are tracking what is the state of the gas. So as it expands, so when the gas moves from this position to this position, you see the volume of the gas changes and the pressure of the gas is also changing. Let us say that state is corresponding to this state here, state 2. Okay, similarly there will be intermediate states. So when we connect all these intermediate states, it gives us what is called as the process path. Okay, now what is our interest? We want to know what is the work done by this gas on the piston during this expansion process. How do we calculate the work done? Okay, so if you look at the piston right now, okay, if you look at the piston, okay, we want to understand how much work is done on the piston by this gas. Okay, so basically we want to calculate what is the force which is exerted by the gas on the piston. So what is the force which will be exerted? So if you want to calculate what is the differential amount of force exerted by the gas, so that will be equal to the pressure of the gas multiplied by the area of this piston. Okay. Okay. And if you want to calculate what is the work done by the gas on the piston, the work done will be equal to basically force into displacement. Or let us say the displacement is the dx displacement. Okay, so the piston moves by an amount dx. Okay, so what is the dw work in that case? The dw work will become, it becomes pressure into area of the piston multiplied by dx, which is pdv. Okay, what is dv? dv is the change in the volume of the gas when the gas is moving by, when the gas is expanding, and the change in the volume because of that expansion is dv. So if you want to calculate what is the total work transfer when the piston moves from position 1 to 2, you can calculate it by integrating it from position 1 to position 2. Okay. So now this work which is done by the gas as it moves from position 1 to 2, this work is basically called as the displacement work. This is also one of the important concept in thermodynamics. Okay. The displacement work, which is also called as a pdv work. Okay. Let's go back and understand a little bit more. Okay. So when we studied about the system, at that time we studied about the system and we told that the system can be classified as open and closed system. Okay. Now let's talk about, and we said that if it is a closed system, then there can be no mass transfer between system and surrounding. Okay. Now there is another concept also. Let's talk about that. Okay. So system and surrounding can interact with each other. Okay. And how can they interact with each other? They can interact with each other via energy transfer. Okay. So energy can get transferred from system to surrounding. At the same time, energy can be transferred from surrounding to system. Okay. So there can be these two, system and surrounding, can interact with each other through energy interaction. Okay. And these energy interactions can be of what type? So there are two types of energy interactions which are defined in thermodynamics. One energy interaction is basically called as work transfer. Okay. And another energy interaction is called as heat transfer. Okay. Heat transfer. Heat transfer. Okay. So system and surrounding can interact with each other via work or via heat. So look at this system, what we are talking about. I told you we are considering gas behind a piston cylinder arrangement. Okay. So this gas behind this piston cylinder arrangement is basically our system. Okay. And this black color dotted line is our system boundary. Okay. Now what is happening? Over the period of time, what is happening? The system boundary is changing. Okay. And what system is doing? System is basically doing some kind of energy interaction with its system, with its surrounding, during this movement of the, or during this expansion of the gas. What kind of energy interaction it is doing? That energy interaction is basically a type of energy interaction which is called as a, is that energy interaction is happening via mechanism which is called as a work transfer. Okay. System, the gas, and the gas which is our system, and surrounding, which is our basically surrounding, in this case you can say everything external to the system, they are interacting with each other, and this interaction is in the form of a work transfer. Gas is doing work on the surrounding. Okay. And this work is basically what kind of work transfer? This is basically a displacement work. Why we are calling it as a displacement work? Because actually the boundary of the system is getting displaced during this interaction. That's why it is called as a displacement work also. And another name is also a pdv work. Okay. Pdv work, that is there. Okay. Now let's see how do we calculate this pdv work for different kind of processes. Okay. When I say processes, what it means, as I told you, the gas behind the piston cylinder arrangement is our system, and this is the state. And how do we fix the state? We know the state of the system when we can completely define the properties of the system. So at this state, we say the state is defined because we completely know what is the pressure and volume of the gas. At this point also the state is completely defined because I know pressure and volume of the gas. And similarly, at this point also the pressure and volume of the gas is completely defined. So this point is my state point 1. This point is my state point 2. This point is my state point 3. And system is passing through all these states during the expansion process. Once you join all these points, what you get is a path. Okay, the system is following this process path when it is moving from state point 1 to state point 3. Okay. And when we are calculating this displacement work, the displacement work is very much dependent on the process path. What kind of process path this system follows while going from state point 1 to state point 3. That is, when the gas is expanding, let us say initially this is the initial position x1. After certain point of time, the piston is moving to x2. After certain point of time, let's say piston is moving to x3. Okay, what is the expansion process, how this expansion process is happening, what is the process path that is happening, that defines what kind of work transfer it is going to happen. So work transfer is very much dependent on the path. Okay, so let how, because if you look at this, in this particular relation, the work transfer is how it is calculated. It is calculated by integration from pdv, and integration between pdv, how it will be calculated, what it will result, it will give you the area under this curve. Okay, it will give you the area under this curve. Okay, so work transfer which is happening during the expansion of the piston from position 1 to 2, that work is pdv work, and that pdv work is basically area under the process path. Okay, now let us see what are the different processes that we can think or we basically have in thermodynamics. Okay, so we will talk about different processes. And as Dinesh sir was also mentioning about the turbines, compressors, like, so right now we are talking about closed system. As we move ahead, we talk about the open systems. And under open system, there are multiple applications. You will see how thermodynamics is playing a crucial role in terms of designing those equipments. Right now, we are talking about closed system where there is no mass transfer, and we are trying to develop the concept of energy interaction. And one of the energy interaction which we are talking about is work transfer. Okay, let's go ahead and look into this. Okay, so now we know that the displacement work is given by this particular relation 1 to 2 pdv. Okay, now important things, students, which you should always keep in mind when you are doing any calculation or something, you should clearly understand what we are writing here. What is p, what is dv, what is our interest, what you are trying to study here. So that is very very clear. Pressure of what, volume of what. Okay, so for that it is very important you clearly understand what is your system, what is your area of interest, what you, on what region you are focusing the intention. So pressure here is the pressure of the gas which you are trying to study here. Volume change or volume is basically the volume of the gas which you are trying to study here. So keep this thing in mind. And when we talked about different processes, the process is process which is followed during the expansion of this gas. Now let us say we are talking about first process. Let us say when the system is moving from state point 1 to state point 2, when I say that, that means when the gas is expanding from state 1 to 2, let us say initially this is the state that we have. Okay, how do we define the state? We clearly know what are the properties at that point. So we know what is the pressure of the gas, we know the volume of the gas. So pressure and volume are the characteristics of the gas. So we know at this condition pressure and volume, so we can clearly define the state. So this is our state 1. Okay, now when the state change is happening or the process is happening, we are talking about the process path. We talked, right, that process path work transfer depends on the process path. Why? Because it is area under the curve. Now we will talk about different process. First process is a constant pressure process. Okay, from state point 2 to state point 2, 1 to 2, when the gas is expanding, the pressure is remaining constant. Okay, the pressure is remaining constant. Under this, if you want to calculate how my system and surrounding are interacting via work transfer, and you want to calculate what is that work transfer you can calculate by this relation. And this relation, nothing, what it gives, it gives the area under this curve. So under this constant pressure process, let us say you want to calculate the work transfer. The work transfer will become what? Work transfer is simple, it is pressure whatever is the pressure, let us say this pressure is P1. You can say here pressure P1, and integral dV is nothing but the volume change V2 minus V1. So for a constant pressure process, you have P at the work transfer is P V2 minus V1. Similarly, let us say now a different process that we talk about. So let us say you take a constant volume process. So if you take a constant volume process, okay, so constant volume process means if you are trying on the PV diagram, volume remains constant, it will become a straight line in this fashion. So let us say you are moving from state point 1 to state point 2. Now, when you are looking at the piston cylinder arrangement, your volume is not changing, it is always constant. So if your volume is not changing, what is the area under the curve? So area under the curve is 0 if you plot it on the downside also. So the work transfer, if you calculate when your volume remains constant. So the first process was pressure remaining constant. Second process we are talking is the volume remaining constant. When the volume remains constant, in that case, what happens? Your dV is 0, so your work transfer becomes 0. So in thermodynamics, we have different kind of process. First, we talked about constant pressure, volume constant. There is another process which is called as an isothermal process. So what is an isothermal process? Isothermal process is a process where our temperature remains constant. Okay, temperature remains constant. So how this process is also defined? This process is defined as PV equal to constant. So this is the relation. Pressure into volume remains constant for an isothermal process. And this condition, which is defined as PV equal to constant. So how does the process will look on the PV diagram? So if you plot this on the PV diagram, so you will get this kind of curve. 1 to 2. So this is the process path. Okay. So you can relate using this process. If you want to relate any two state points, how you can relate? You can write P1 V1 equal to P2 V2. Okay. Look at it here. During the expansion process, what is happening? Okay. During the expansion process, when the gas is expanding from position 1 to position 2, V1 to V2, we know V2 will be greater than V1. So what will happen? Pressure P2 will be less than P1. So that is what happens in an expansion process. So when gas expands during an expansion process, your volume increases and pressure decreases. So if you use the same relation, right? If you use the same relation for an isothermal process, you can calculate what is the work transfer. So work transfer, it will come out to be P1 V1 in log V2 by V1. Okay. Now we will draw a general chart and probably you will understand for different processes. Let me explain. So, so let me draw a general chart here. Pressure versus volume chart here. Let us say this is my state point 1. I am drawing different process. So this is constant pressure process. Pressure remains constant. Okay. And I am doing right now an expansion 1 to 2. So when I say expansion, pressure should decrease. Again, this is my constant volume process. Okay, this is my isothermal process. PV equal to constant. Similarly, there are other processes which are defined by this relation between pressure and volume, that is PV to the power n equal to constant. Okay, so this is the relation between pressure and volume for a process which is called as a polytropic process. Okay, polytropic process. Here n is basically an exponent. Okay, n is an exponent here. Okay, so for a polytropic process, if you calculate the work, okay, so how do you calculate the work? Again, the same relation you have to use, integral 1 to 2 pdv. Okay, and you can use this process path relationship. So what PV to the power n says is that the state point, any two state point, if you want to connect along this process path, like let us say this is the state point 2, this is the state point 3, they follow this relation, this mathematical relation among pressure and volume. So you can relate the two state points. You can say P2 V2 to the power n is equal to P3 V3 to the power n. So they are connected by this relation. Similarly, for an isothermal process, let us say you have different state point. Don't confuse. These are two different. These are 2 and 3, which I am writing. I will write here 2 dash 3 dash. For an isothermal process, these two state point, they are connected with this relation, PV to the power constant. Okay. So it will be P2 dash V2 dash equal to P3 dash V3 dash. Okay. So for a, let us say for a polytropic process, if you want to calculate the work transfer, right? So what relation you get? So you can figure out the math here. You can replace the pressure with C V to the power n relation and substitute and then perform integration. I will just write this, probably not go through the entire mathematics. You can figure out the mathematics. I'll just write the simple formula here. So you can perform this integration, and once you perform the integration, you can calculate the total work, which will be P1 V1 minus P2 V2 over n minus 1. So for different processes, you see you get different expressions for the work transfer. So what do we understand from here? If we are talking about work transfer in thermodynamics, is work transfer dependent on the process path, or is work transfer independent of the process path? So when I do the figure out the process path, the work transfer for different process, what is happening is that I'm getting different relations. Okay. And also if you look at, if you try to plot the area, because what is work transfer? Work transfer is basically area under the curve. Okay. Area under the curve. Which curve? Area under the process path. So if you look at between 2 to 3 and 3 to 4, between different process path when I am having, right, the areas are different actually for different process path. Okay, if I go with one path and then if I go with this other path, the area under the curves are different. So what it indicates, what it is indicating about the work transfer mechanism, let's understand this with a different diagram. Okay, this is a general diagram, let us say, if we try to plot here. So this is PV diagram, let us say. Now what we are trying to understand is a relation for the work transfer. We want to question whether the work transfer is dependent on the process path or not. So we now saw the relationships for calculating the work transfer. Now what I am doing, I'm taking two state points, state point 1 to 2. The system is going from state 1 to 2. In one case, it is following this process path, that is the process A. In the second case, let us say system is also undergoing the same state of change, but it is following a different process path, that is point B. So in first case, it is going through a path A. In second case, it is going through a path B. Now you will be confused. What is A and B? Again, go back. When I am drawing this, like imagine, you should be clear what you are trying to do here. This path, what you are drawing, what it is indicating for you. You should be very clear. Okay. What is your system? Understand. You should be clear. Gas behind the piston cylinder. Let us say again the same standard example I am taking again. This is my system. Okay. This is my, let us say, state 1. Now what is happening? Gas, let us say it is expanding. After it expands, let us say this is my 1 dash position along the process path. Just imagine what is happening. So after certain point of time, piston has moved to a new position. At that new position, the pressure in the gas has changed, volume of the gas has changed. Okay. And let us say you are executing this process from state 1 when the piston is at position x1 to the condition when the piston has moved to the position x2. So during all these state changes, you are trying to record it and you are trying to plot the path. So in one case, this is the path, and in one case, this is the path. Okay, but you are reaching the same end state. Okay, so if we question ourselves, let us say from 1 to 2 if I go by path A, and 1 to 2 if I go by path B, and if I calculate the work transfer, whether I will get the same work transfer or different work transfer for both processes. Okay, is my work transfer dependent on the process path, or it is dependent only on the end states? So look at it, very, very simple. Again, I will draw here the curve. Look at it here. So this is my volume. This is my pressure. Okay. So I am just demarcating it, my curve. So first curve is 1 to 2. So if I want to calculate the work transfer is simply the area under the curve, which is this. So in one case, this is my work transfer. In the second case, let us say I just want to draw it here. So this is my process path A. In the second case, this is my process path B, which is there. So in that case, the work transfer is there. Okay. Now what happened? I am moving from say between the same two end state. I am following two different paths. When I am following two different paths, what I am getting? I am getting different magnitude of work transfer. Why? Because area under the curve is different for the two different processes. What it says? Clearly says one thing. That is my work transfer. It is depending on my process path. It is very much dependent on the process path. Okay, so work is what kind of a function? I can say work is a path function. So work transfer is a path function. The path function because it depends on the path. Okay, now let us try to understand about one more thing. So we discussed about that work transfer is a path function. Let us say if I want to ask you what is the change in pressure, what is P2 minus P1? Okay, or what is V2 minus V1? Okay, when I go by path A and when I go by path B. Similarly here, when I go by path A and when I go by path B, do I get the same answer or do I get the different answer? Okay, if I am calculating P2 minus P1, and what is P2? P is my a property of the system. V is also a property of the system. So when I am calculating the property change, okay, when I am calculating the property change between the two states, what is the property change between the two states? Is the value of the property change dependent of the path or independent of the path? Let us say if I calculate from path A, I will get answer P2 minus P1, path B, P2 minus P1. If the pressure here, let us say is 100 bar and this is 50 bar. Here volume is, let us say, 1 meter cube. This is 2 meter cube. If I calculate from here, I will again get 50. Here 50. Here I will get 1, again 1. What it indicates? It indicates that properties, the properties of the systems are basically point functions. These are point functions. When I talked about point function, what does point function means? When you want to evaluate the property change, okay, it depends only on the end state. It doesn't depend on the process path. It doesn't depend on the path. So that's why properties are point function and work transfer is a path function, because for different processes we get different work transfers. Okay, if this is clear, then we move to the next important concept in thermodynamics, which is I am always talking about, guys, system, and what I am always giving you an example, gas behind a piston cylinder arrangement. Okay, now how do we model the behavior of this gas behind the piston cylinder arrangement? How do we say this thing? What is this behavior of the gas? Is there a model for something? So in thermodynamics, when you are studying, right, you will again encounter a very popular model which is used for these gases, especially which is called as an ideal gas model. Okay, ideal gas model. Okay, so what is an ideal gas model? A very important terminology. Okay, what is an ideal gas model? Again, standard. I will give you same example behind piston cylinder arrangement. Okay, okay. Take my piston cylinder. Take the piston cylinder arrangement. Take this gas. Okay, okay. At one state point, my pressure is P1, volume is V1, temperature is T1. Okay. After, let us say the gas has expanded and it has moved to the new state. Okay. Same gas, now it has expanded and moved to the different state. Its pressure is P2, V2, and T2. So, what is an ideal gas model? Ideal gas model is a model that relates the pressure, volume, and temperature of the gas. Okay, so it gives us an equation which relates pressure, volume, and temperature of the gas. So, what is the ideal gas model or ideal gas equation? Ideal gas equation, PV equal to MRT. Okay, what is P? P is the pressure of the gas. In thermodynamics, always the pressure when we are talking is the absolute pressure. Okay, V is the volume of the gas, M is the mass of the gas, R is the characteristic gas constant that is specific to the gas, and T is the thermodynamic temperature of the gas, which is also specified in Kelvin. Again, how do you calculate R? R, as I have told, this is the characteristic gas constant. Characteristic gas constant is related to universal gas constant by a relation RU by M, where RU is your universal gas constant. The value of this is always constant. This is 8.134 kilojoule per kilomole Kelvin. M is your molecular weight of the gas. Okay, this will have different values. So when you look at the tables for hydrogen 2, oxygen different values, nitrogen different values. Okay, so this is in kg per kilomole. Okay, so if you substitute this relation here, right, to what do you get? PV equal to, let me replace this relation, M. So I will replace, so you get RU by M into T. So PV equal to, okay, so M by N, this is your number of moles of the gas. So these are the two equations. One equation is this for the ideal gas, which is where the mass is specified in kgs. This is the another equations where we are dealing with the, when we solve the ideal gas relations by using the moles, number of moles. So these are the second relation. Okay, this is first relation, this is the second relation. Now let us try to understand from the ideal gas relation different processes that I talked about. Okay, so let us write the ideal gas equation of state, PV equal to MRT. Okay, so for an ideal gas, let us say for an ideal gas, when your temperature is constant. For an ideal gas, when temperature is constant, what do you get? PV equal to constant. Okay, PV equal to constant. Okay, so for an ideal gas, PV equal to constant. So how it this two state point, as I told, how they are going to relate if you are drawing it on the PV diagram. So let us say this is the process path, this is state 1, this is state 2. When I am talking about a constant temperature process, which is also an isothermal process. So during this entire process, my temperature remains constant and any two state points are related by this relation P1 V1. So I can relate here P1 V1 with P2 V2. Now, so this is an isothermal process when I am considering an ideal gas behavior. Now I want to talk about the other process. Okay, let us say we talked about the polytropic process, PV to the power n equal to constant. So this is the polytropic process. So system is undergoing a polytropic process and this curve is now PV to the power n equal to constant. Okay. So we know between any two state points, if you want to relate, how you can relate, these will be related by this relation P1 V1 to the power n equal to P2 V2 to the power n. Simple mathematical relation for the curve, and you can relate P2 by P1 with V1 by V2 to the power n. Important question now comes. Let us say you want to relate the temperatures with pressure. How do you do it? Very simple. So you can use ideal gas equation PV equal to mRT. Why you are using ideal gas equation? Because we are considering the gas which is undergoing this process is now an ideal gas. So then if I replace now, let us say if I replace pressure here with mRT by V, what do you get here? You get mRT by V into V to the power n equal to constant. So you get T V to the power n minus 1 equal to C divided by mR. Okay, so this is also a constant because mass is constant for the gas, R is constant for the gas. So you get this relation TV to the power n minus 1 equal to some other constant K you can say. So you can say T1 V1 to the power n minus 1 T2 V2 to the power n minus 1. This is another relation which you can get from here. Okay. So these are the different relations that we get. Now I will briefly introduce the concept of first law of thermodynamics to help you understand the design part as Dinesh sir was talking about. So what is first law of thermodynamics? Okay, sometimes students have a lot of difficulty in terms of understanding it. Okay, so what we do is this is our system. Okay, when I draw system, don't get confused that I am always taking an arbitrary thing. You can think in terms of a gas. Okay, right now think in terms of, again, imagine the piston cylinder arrangement and gas behind that. Okay, so this is my system. This is my surrounding. Okay, and this is my boundary. Okay, this is my boundary of the system. Okay, system and surrounding are now interacting with each other. As I told you, they can interact via, there can be energy interaction. So system and surrounding can interact with, can transfer energy. There can be energy transfer from system to surrounding and surrounding to system. Okay, so what does first law of thermodynamics gives us? First law of thermodynamics is basically law of conservation of energy. Okay, so how do, what is the, so let us say this is the energy coming inside the system, total energy coming inside the system. This is the total energy going outside the system. Okay, out. Okay, and this is the total change in the energy of the system. Okay, okay. So how do you relate? What is the basic principle? So in terms, so what you can write, first law, law of conservation of energy, how we write it in the simple mathematical form, it will be total energy coming inside the system minus total energy going outside the system is equals to change in energy of the system. Okay, change in energy of the system. Example to understand is in terms of the bank balance. Let us say starting of the year you have 10 rupees. Okay, now what you do, constantly you are transferring energy. or not energy, money into the system. So every month you come and you keep transferring 50 rupees. Okay. At the same times, every month you keep taking 10 rupees. Okay. So what will happen? So you are always adding more and taking out less. What will happen to the net money inside? So money will increase. Okay. So let us say if E1 is my initial state. Okay. And let us say system is undergoing a change of state from E1 to E2. Okay. And change is what? Change is E2 minus E1. Okay. So what will happen to E2 minus E1? Net energy of the system. The energy of the system will increase if more energy will be coming inside the system and less energy is going outside. Energy of the system will decrease if more energy is going outside and less is coming inside. Okay. So this is a very, very simple or basic definition. Okay. In terms which you can relate in terms of the bank balance. Okay. Now, what are the ways in which energy can come inside the system and go outside the system? In thermodynamics, there are only two energy interactions which are defined. Okay. So energy can come inside the system via heat transfer. Okay. Okay. Because of the heat transfer, there can be energy interaction between the system and surrounding. So energy can be exchanged between system and surrounding via heat transfer. Second is there can be work transfer between system and surrounding. Okay. And third thing, energy can also be transferred between system and surrounding. Now I extend it little bit because of the mass transfer. Okay. Mass transfer. So there is mass coming inside the system, there is mass going outside the system, which we are talking about open system, in which mass which is coming inside it is bringing energy and mass which is going outside is taking energy with it. So these are the three mechanisms in which the energy can be exchanged. So this you can write it in this form: E in minus E out is equals to delta E, where delta E is the energy of the system. This E is the energy of the system. And this E in E out are the energy interaction between system and surrounding. Okay. So this I can write it in this form. E in equal to delta E plus E out. Let us say energy coming inside the system. We say this is heat which is coming in. Let us say there is Q coming in the system, and there is W going outside the system, where Q is my heat transfer and W is my work transfer. So I write Q, which is coming in, delta E is the change in energy of the system, plus what is going out is W. Okay. So this is your first law definition for a process when a system undergoes a process. So Q is equals to delta E plus W. You would have written this term multiple times, where Q is net heat transferred to the system, W is net work done by the system, delta E is the change in energy of the system. And delta E, what is the energy of the change in energy of the system? What the different energy system can possess? System can possess kinetic energy, system can possess potential energy, and system also possesses what is called as internal energy. Kinetic energy is due to the motion. There is a bulk motion of the system. Potential energy it is at a certain elevation with respect to the gravitational field. Internal energy, why internal energy is present in the system? Internal energy is present in the system because of the, this is the energy stored at the molecular levels. Okay. So kinetic energy is there is a bulk motion. Potential, there is a elevation with respect to the in the gravitational field. Internal energy is because of the energy stored at the molecular level. So at the molecular level also, there are molecular activities which are happening. Okay. So if you look at the molecules, they are continuously in random motion. So they possess rotational kinetic, they possess translation kinetic energy. They are also rotating, so they possess rotational kinetic energy. So if you want to sum up the total energy of the system, so energy of the system will be sum of kinetic, potential and internal energy, and change will be change in kinetic, potential and internal. So this is the definition of first law of thermodynamics, which is a general definition which can be applied to open system and closed system. Okay, so I will end the session here. So this is the just a brief gist or introduction that I have given in for the thermodynamics. When we go for the complete sessions or complete things, we cover every aspect in very detail with lot of numerical examples and uh, discussions.
Yeah.
Dinesh sir,
So I
anybody has any
think,
question?
so guys, any question? Vinayaka, Ananda, Nirja, others? I think they need to brush basics. So once we start subject, they will be in better situation to ask more questions, sir. Yeah. So
Okay,
thank
sure.
you, Pradeep sir. You can go to
Thank
end
you.
slide and we can wind up the session.
Okay,
Thank
sure.
you.
Let me just sorry. Give me 1 minute, sir. Yes, sir. Thank you, sir.